this video, we are going to learn how to write a model for a CRD, or completely randomized design, with a factorial treatment structure consisting of 3 factors. We will also discuss interactions amongst the factors and check all ANOVA assumptions necessary. So let's get started with an example. Today's experiment is studying the effects of cooking time of row pulp, percentage of hardwood concentration in the pulp, and vat pressure on the strength of paper. There are 2 levels of cooking time, 3 and 4 hours, 3 levels of hardwood concentration, 2, 4, and 8%, and 3 levels of pressure, 400, 500, and 650. Each of the 18 total treatments is replicated twice within this study. With 3 factors, we must include the necessary interaction terms to determine their significance. So there will be 3 two-way interactions and 1 three-way interactions amongst all the variables. So let's move to JUMP to start making this model. In JUMP, after we enter our data, we can now make a model by adding our desired response variable, as well as each of the individual variables, followed by each variable crossed with each of the other variables. And finally, a variable with all 3 factors crossed together. But before we even begin analyzing our results, let's first make sure our ANOVA assumptions are satisfied. The 3 biggest assumptions of concern to us are that of independence of errors, equal variance of errors, and the normality of errors. Independence of errors does not really have a formal test, so we hope that the use of random assignment as well as randomization of run order will eliminate possible dependencies in our data. Yet we can use JUMP to check the assumptions of normality and equal variance of errors. Starting with the equal variance assumption, we simply analyze the residual by predicted plot given by the model. Here we do not see any fanning shape or atypical patterns, and the data points all appear random. So we have no reason to believe that the data has unequal variances. Lastly, we check the normality assumption. So let's save a column in our data table of the studentized residuals. And then we look at the distribution of those studentized residuals and produce a normal quantile plot. Here we can see that the data appears to follow a mostly normal distribution, but let's run the formal test to be sure. Once we find the Shapiro-Wilks p-value, here being 0.0472, we can conclude that there is no reason to believe that the data does not come from a normal distribution. So now that we are confident that our assumptions have been met, we can begin constructing our model. The generic formula for our effects model appears as follows. Let's call the cooking time of the pulp factor A, or alpha, hardware concentration of the pulp factor B, or beta, and vat pressure will be our factor C, or tau. Now I know this looks really daunting, so let's break it down by term. The response term, Yijkn, represents the nth response at the ith level of cooking time, jth level of hardwood concentration, and kth level of vat pressure. With 2 replicates per treatment combination in this study, the values the subscript n may take are 1 and 2. Mu represents the overall mean response of strength of paper regardless of cooking time, hardwood concentration, or pressure. Alpha I represents the effect of the ith level of cooking time on the response of paper strength. This means that the values the subscript I may take are 1 and 2, corresponding to the number of levels of cooking time. Beta J represents the effect of the jth level of hardwood concentration on the response of paper strength. This means that the values the subscript J may take are 1, 2, and 3, corresponding to the number of levels of hardwood concentration. Tau K represents the effect of the kth level of vat pressure on the response of paper strength. This means that the values the subscript K may take are also 1, 2, and 3, corresponding to the number of levels of pressure. The next 3 terms following each individual effect represents a particular 2-way interaction between variables. For instance, the first interaction, alpha beta ij, represents the interaction between a specific level of cooking time and a specific level of hardwood concentration. The last of the interaction terms represents the 3-way interaction between all of the variables at specific levels of each. Finally, epsilon ijkn represents the error term of the nth response at the ith level of cooking time, jth level of hardwood concentration, and kth level of vat pressure, assuming the errors follow a normal distribution. Now that we have constructed our model using JUMP and understand each term in our effects model regression equation, We can form our model using these parameter estimates jump calculated for us. Each parameter estimate is equivalent to the effects seen by our factors either individually or within their interactions. From the list of all effects given within these parameter estimates, we deem a term significant if its respective p-value is lower than the stated confidence level of 0.05. In our example, we see 8 factors and interactions which are deemed significant according to their p-values, and thus we include these in our model. As a result, our final model for this example will look like this, where the estimated paper strength is either increased or decreased from a constant according to the treatment combinations being used. As you can see by the matching colors, each term from our parameter estimates correspond to a particular factor combination at a specified level. In sum, we learned how to check assumptions and create a model for a completely randomized design using a factorial treatment structure. Thank you so much for watching. Bye.